Hello everyone, I'm Amir. The paper that we are going to present today is generating evolving property graphs with attribute of a preferential attachment. In this work, we make progress toward the data generator for evolving graphs, which represent graph topology and vertex edge attributes. Our ultimate goal is to create a standardized benchmark with predefined queries to measure performance of evolving graph databases. So first, we will have an introduction. I will define what graph is, what evolving graph is. Then we will look at two graph evolution model, random walk and recursive search. Then we will look at how our model attribute-based preferential attachment, or ABA, is different from those, and then we will show you a case study on graph generation. Graphs are used to represent many phenomena such as transportation network, social network, the web, collaboration network, and so on. These phenomena can change over time. New vertices can get added, new edges can be created, some attribute might change, even some node or edges might be removed from the graph. Also, graphs can have properties, they can have attributes. It's not just about topology. Both edges and vertices can hold any kind of attributes such as any other databases. We need a scalable system for query and store those evolving graphs. We are already working on such systems. We named it Portal. To measure the performance of that system, we need a standardized data set. We can always use real graphs, but real evolving graphs is hard to find. Usually they don't have attributes. Also, it's hard to control the different characteristics of those graphs. So there is a need for us and anyone else who are working on evolving graphs to have a synthetic model to be able to generate graphs and benchmarks. There have been works in this area. One trend of work is looking at the evolutionary of graph topology. Two famous models in this area is random walk and forest fire. Those models solely focus on the structure and they don't use attribute in their evolution. Another interesting work is LDBC social network benchmark. I think there have been few talks on that in the SIGMOD this year. They generated a realistic synthetic social network with attributes and different type of entities. The missing part of their model for us was they're not using any principal evolution model. They just generate timestamp in an almost random way. Attributes. Why does attributes matter? Look at this graph. If we look at just the topology of the graph, creating the red edge makes complete sense. But if we add attributes, for example, put Albert Einstein in one of the nodes and William Shakespeare on the other one, and assume it's a collaboration graph, what would those two work on? To be or not to be, that's the general relativity. That makes a good title for a Hollywood movie, but not for a research paper. Random walk and recursive search. We build our model on random walk and recursive search models, so it would be nice for us to look at those. Random walk consists of two steps, node creation and edge creation. Assume that we have a graph. In node creation step, we will create a new node and we will randomly connect it to one of the existing nodes in the graph. Then we will go to the edge creation step. The node will start a random walk and graph, start visiting new nodes, and based on the probability, it will decide whether if to create a new edge or not. Here we assume that it did. Then it will follow its random walk. Whenever there is no other path to continue, or we decide not to create a new edge, we will go back to the node creation step and add a new node. Recursive search follows the same pattern. same concept, but instead of searching one path, it will recursively search all the paths possible. Basic block of random walk and recursive search can be looked as closing triangles. A triangle is a clique of size 3. Here we close a triangle by connecting x to z, which has a path of 2 by creating edge xz. We will use triangle closing for our model, so we needed that. Let's look at our model and how it's different from recursive search and random walk. So in random walk, we will only add one new node at each iteration. Instead, since we wanted to build large-scale graphs, we decided we will do it in a batch mode and add multiple new nodes at each iteration. Another difference between our model and RW and RS is that in RW or RS, each vertex creates all of its edges at single iteration. It makes sense for some graph like citation graph when you cite everyone then publish your work, but it doesn't for social network, collaboration graph, and many other graphs. So instead, in our model, we try to close all the possible triangles at all the iterations, which you can see. The most important difference is that random walk and recursive search create their links with a fixed probability. But we are assuming that is not correct. If two nodes are more similar together, we should have a higher probability for creating an edge. So here, for example, it will be more likely for Albert Einstein to form a link to Isaac Newton instead of William Shakespeare. At least they are both physicists. We implement our generator model using Apache Spark and a Hadoop cluster. We also use GraphX, which is a library in Apache Spark. And we use a portal system for some part of the implementation. Using Spark enabled us to run the code on a cluster setting, so we can do it in a distributed way and we can generate larger graph in a faster way. Okay, let's look at our graph generation process. So, as I said before, graph generation consists of two steps: node addition and edge creation. In this work, we are not looking at node addition and we are focused on edge creation process. For a case study, we extracted a grow-only graph from DBLP dataset. In our graph, vertices represent authors. Each vertex attribute is venues where that author has published papers, and each edge represents a co-authorship. For example, looking at Julia, she published a work in VLDB, so for her attributes we would have VLDB. Then in 2006, she didn't publish any new work, at least not any new venues. Then 2007, we have WebDB. So we add WebDB to the attributes of Julia's novel. We looked at triangle closing probabilities and the real DBLP graph based on similarities. We bucket the similarities to 3 buckets. Also, we calculated the unconditional similarity here, which is just all the triangles that close divided by all the possible triangles. So as you can see, if we have more similarities, it will be more likely for a triangle to be closed, but for less similar nodes, it will be less unlikely, even less than unconditional. Using those probabilities, we generated models. Here on the upper figure, you can see number of edges generated. The blue line is DBLP, which is the original graph. The red line is when we use attribute similarity. And the green one is the structure model when we use the unconditional closing triangle probabilities. So as you can see, both of those a structural and attribute-based model are following the same trend, number of edge, based on the number of edge. But our main difference is that we are producing more accurate and more realistic edge than a structure-only model. To show that, we recalculate the probabilities same as this slide, and then we compare those using a mean square where each bucket to each bucket-wise. Our model is, sorry about that. Our model has lower error rate and it's more stable. In the structure where the error is higher, also it's some kind of random. After that, we decided to use the generated graphs in our system to test few queries, to get some more insight about the graph we generated, and to make sure that the graph we generate is valid and correct. We wanted to make sure we haven't generated some garbage. So we run two queries. The first one is average degree, and the second one is clustering coefficient. We timed those experiments. Since the nodes are coming from the real DBLP and the number of edges is similar, all the experiments have same execution time. But our model has better degree prediction, and even for clustering coefficient, we are closer to the real graph. So, in this board, we presented a data generator for evolving properties graph. None of the previous board, as far as we know, have studied how attribute would affect the generation process over time. We show that attributes play an important role in edge creation. In future, we are planning to work on node creation process. We want to be able to create nodes, automatically attach those to existing graph. We want to be able to evolve the attributes. That's one of the work that has not been done yet. And at the end, we want to define a workload of evolving graph query and analysis primitives to have a complete benchmark for anyone who wants to use such system. Our portal system source code is right now open source and available. I will try to open source the data set and this part of the code hopefully by end of June or mid-July. Thank you.
Okay, we have time for questions. Let me ask a quick question. So, how large are the graphs that you're producing in terms of number of edges, number of nodes, and how long does it take?
Okay. I wish I had the paper with me. It has it's the same size as original DBLP dataset since we are bringing the actual nodes so we cannot generate any new nodes. It's the same as DBLP size. And for a structure only, it takes few minutes. For an attribute base, since you need to calculate similarities between sets, it's a slow process. It will take less than an hour, I think. If you look at the paper, the actual timing is there.
And how much better is this than just like, I mean, when I do data generation, I usually just use statistic like properties and statistic distributions. So could you also create a structure using this, or do you really need the edge construction? What additional features does it give you?
So we are working on graphs, and graph follow, they're not same as generating raw data in the table. In a classic way of database, they are following power law rules. There are other rules that they show over time. For example, the diameter of the graph will change. You cannot randomly generate a graph using a statistical model. It won't work. Even we tried to sample the graph randomly and the result was horrible. It was something completely different. So if you want to generate or sample a graph, you need methods such as random walk or something iterative that conduct exploration of the graph. It's not as easy as just randomly selecting or generating.
So one question. So I was wondering, so what is your main target? Is it more performance testing of graphs, or is it really functional testing? So trying to generate data such that you can cover different cases that an application would do. Because these are very orthogonal, and from what you presented, I was quite not sure what the target is.
It was a word-to-word generating and standardized benchmark for evolving graphs. Such thing actually doesn't exist. There are few systems working on that. But
okay, the benchmark then also includes certain, so let's say, representative queries over the data you generate.
Yeah, this is a primitive word. We are still
okay, no, I was just wondering where you want to go.